Let us continue with design of footings. Last class we have started the basic philosophy of design of footings. If you see for any reinforced concrete design, not only reinforced concrete design, for any structures if you have to design, so for the governing one you have to isolate that for an element what are the governing forces acting. In the footing case we have bending moment, and shear forces. Other one is shear force. So, what we have seen in the last class, if we have a column and we have to provide the foundation, it may be rectangular, it may be square also. Our objective here that we have to, due to this axial load say P, or due to say your moment, due to your axial load or due to say moment, we have that pressure here. Now bending moment, the critical sections. For bending moment, it will be in the face of column. That means either it will be here or we can take it here. So face of column. For shear force, we have two cases. One is called one way. So that one will be at a distance d from face of column. So it will be certain distance, say here d, where you have to calculate that shear force and that we have to check. The other one is called two ways or punching shear. In this case, that is as d by 2 from face of column. So these are the three cases that you have to consider. We can start with that bending moment. We can calculate bending moment at this face and we can find out. So first step, just let us recapitulate. First step, that what is the load you have, and that should be the characteristics load. It's not the ultimate load, because we are not taking the ultimate bearing capacity of soil. We are taking the safe bearing capacity of soil. You can say that is the serviceable one. So the load you will take it here, that P, that is not multiplied with 1.5 or whatever it is. So that is the first difference, because otherwise if you multiply with 1.5, your footing size will be bigger. So that you should remember. So your column load and that's certain amount, say maybe 10% you can take for the footing, because footing size already you have not yet decided. So 10% of the axial load whatever coming, you can take it as the self weight of the footing. So considering that, you can find out the footing size under serviceable condition. Next one, you have to do it, you have to design for, that means you have to provide the section size. You know the area of the footing, it may be rectangular, it may be circular, it may be square, depending on the situation. Now what you will do, now you have to provide the depth of the footing. This depth of the footing you have to provide. That is the first one, that you have to provide the depth of the footing, overall depth. 50 millimeter we have to provide the clear cover, that you should remember. Then we have to provide reinforcement. So reinforcement for this type of thing, you can consider this one as a slab. You are not providing any shear reinforcement, no shear, no stirrup. Only you are providing, say, your slab. So here that critical stress for tau c, that will be, say, less than, say, 0.35. It should be less than 0.35. That you should consider, because if it is more, then you have to provide shear reinforcement. But generally in this type of footing, we do not provide any shear reinforcement. There is no provision for that. We could do it, but we don't want to do it here. So that's why the only alternative you have, that you change the, increase the depth, so that your tau c becomes that, or the shear stress developed, that is less than 0.35 Newton per square millimeter. So what you have to do, we have to check out of this. We have to start with one of them and then you have to check. Generally it is very much, say, if you see bending moment, shear forces, out of that you will find out the shear force mode. That means taking bending moment, whatever depth you will get it, and taking shear force, whatever depth you will get it. Out of that, shear force, that depth computed from the shear forces will be more than the depth computed from the bending moment. That's why in this case we start from the shear force and then we check for others. That we do. Compared to your slab or your beam, we generally start with, say, your bending moment and then we check with the shear. Here, depending on the situation, you will find out, because we can start with the bending moment, but later on you have to increase the depth for shear forces. It may happen, and that's why we start with the shear force, maybe, say, for one way. So this is your whole thing, whatever we have to do, and let us start solve one, say, square footing, one problem. So design of square footing. Dead load, let us take. Imposed load, and a square column that which we have to support. Let us take that this is having, say, we are not interested for that. So let us take, say, 25 millimeter bar provided. In the columns, concrete M20 and steel Fe415. Bearing capacity, let us write down safe. So which is coming as 200 kilonewton per square meter. So this is your, that your parameters. You can understand that how that imposed load or live load is 500 kilonewton, where a dead load which is coming as here, say, 1100 kilonewton. So you can understand that what is the ratio. So almost it has become more than the double, that your imposed load. That means this is our objective. We have to support this load, say, 500 kilonewton, say. That is the main part of the any structure you are going to construct. So for that, the overhead, you can say, that means overhead here it is coming, say, 1100. So for a structure, if you consider at least for, say, your bridges, this is one of the important part. Say the span of the bridge, if you take, say, span of the bridge, if it is, say, less than your live load or vehicle load, because that is the objective for making a bridge. So vehicle load, whatever is coming, and the dead load of the structure of the bridge, if for a small span, maybe, say, 20 meter, or, say, you can consider, say, 15, 20, 30, like that, you can compare, that is almost, say, 1:1, something in that ratio. but if it is more, maybe 100 meter, all those things, then you will find out that vehicle load, whatever coming, that is very less compared to the dead load. So that way I can say that because what I mean to say that dead load, that one to support the structure, to make the structure, if it is say 50-50, we can say it is economic or optimum, but most of the cases you will find out it is not at all possible to make it economic. In this case, say here, finally at the end you are coming to that dead load and live load ratio, that is you are almost a 2:1. Anyway, and on the basis of that one can estimate that your say cost, other things also one can estimate. So load equal to 1.0 times dead load plus 1.0 times live load plus self weight. Okay. So which comes as 1100 plus 500, and let us take 100 kilonewton as self weight. So which is coming as 1700 kilonewton. Area of footing (1700) divided by 200, which is coming as 8.5 square meter, equal to 2.915 meter into 2.915 meter. So we can find out, let us provide size of footing, say 3 meter or 3000 millimeter times 3000 millimeter. So we shall take a square footing of 3 meter by 3 meter. We can calculate depth so depth from one way shear, say what we are assuming that minimum shear, though it could be less 0.28 something, but since we are using say tensile steel, so because of that we can increase little bit your say shear stress. So minimum shear stress that is permissible here in our case, that is 0.35 Newton per square millimeter. Okay. Now Q is the pressure, that one should be equal to P by L square. Let us find out. We are taking so we can take it and we are interested to find out at a distance D. So this distance from the face of the column, that is D. So what about this length then? Let us take this length. This is your L, and column size, square column A. So this one will be equal to L minus A by 2. Okay. So what about the shear force here then? The shear force here, just let us make it like this. Okay, yes, yes. So L minus A sorry, just a minute. Let me since I have already written here, so please correct me what I can do just to keep it. So let us make this one, then you do not have any objection, I hope. Okay. So I mean to say this is from the face of the one. So L minus A by 2. So this is your A, and we have the uniform pressure, and that is Q. So V will be equal to the shear force V along this line. There are two ways we can make it. One we can take unit length, or other alternative that we can take the full length. This is also L. So V will be equal to that Q times L, that means a unit strip per meter one, I can take it, say, times L minus A by 2 minus D. Okay. So I can take it here, L minus A by 2 minus D, that we can take it. So that is your, say, shear force. So we can write down it as so this is the shear force we are getting it here. Equal to, we can write down P by 2L, L minus A minus 2D. This is your the shear force V along this line at a distance D from the face of the column. So we can write down it as, what about the shear force that is permissible? So that shear force permissible, that is here. So this is your, say, D. We are taking that effective depth, say, small d here. So shear force, that whatever shear force developed here, that should be resisted by the cross section here. So that cross section equal to this A length times that effective depth times, so L times D, that is the area which is resisting, times that tau C, that is permissible. So that is the shear force. So we can write down, and that should be resisted, that means, so these forces should be resisted by that shear force. So we can write down as tau C times L times D equal to P by 2L, L minus A minus 2D, or twice tau C L square D equal to P times L minus A minus P times 2D, or tau C L square D plus P times 2D will be equal to P times L minus A, or D equal to P by L minus A divided by twice P as twice tau C L square. So the final form we can find out it as D equal to P L minus A to P plus tau C L square. So we can find out, we know P, L also we know, A the column size, that also we know, tau C 0.35 Newton per square millimeter. So we can find out the depth. What about PU, that design load? (1100) plus 500, 1100 dead load, 500 live load plus self weight times 1.5 equals 2550 kilonewton. We can write down now D will be equal to 25, let us make it like this, P times L minus A divided by twice P plus tau C L square, P or PU we can write down here, PU 2550 kilonewton, L 3 meter, A 0.45 and tau C 35 Newton per square millimeter equal to 350 kilonewton per square meter, that is your tau C. So we can write down as 2550 3 minus 0.45 divided by 2 times 2550 plus 350 times 3 square, which comes as 0.570 meter equal to D equal to 570 millimeter. So D equal to 570 millimeter, that we are getting it here. Now we can check with the two-way shear. So depth required for two ways shear, or which we call it say punching shear. So critical section at D by 2 from face of the column. Let us draw a figure here. So this is the critical section, and this is at a distance D by 2. What about the perimeter? A plus, this is A, so A plus D by 2 D times 4. So we can write down here, if we consider the equilibrium forces, so we can write down Q or P by L square minus A plus D whole square. We are taking this portion, we are taking it out, so we can say this portion will be equal to 4 times A plus D, that is the perimeter, times the D. D is the effective depth, because we are talking this one. Please note that whenever we are talking, say which one will be resist, it will resist this one. So we are taking the perimeter, this is your perimeter, which is here for, this is rectangular, but we are talking say square. So 4 times A plus D times the, not the overall depth, it should be effective depth. So that cross sectional area we are talking, okay, and then remaining portion whatever there, that one whatever forces are coming, that we have to take. So 4 times A plus D times D, that's what we are getting it here, and we have to take times, but here it is for punching shear. So tau P equal to, our code says it should be equal to 0.25 root FCK. So that means there is M20 grade of concrete, so we know that what is the allowable punching shear. So what we can do it here then, we can now calculate. Instead of doing that, we can simply put the value of D here. D equal to 0.57, already we have got it. So now when we have got the 0.57, now on the basis of that, if we know this portion, then I can check what is the value of D. That D we can find out, and if that D is less than 570 here in our case, then we can say it is all right. Otherwise you have to increase it. Other alternative could be that again we can make it that full from D square, all those things, from there also you can calculate D. Since already we know that 570 millimeter, so that we can keep it here and we can check whether that D is coming less than the 570 or not. So perimeter equal to four times 0.45 plus D equal to 0.57, we have got it, which comes as 4.08 meter. Q equal to P by L square equal to 2550 divided by 3 square equal to 283.333 kilonewton per square meter. Shear force P by L square minus A plus D whole square equal to 2550 divided by 3 square. So 3 square minus A equal to 0.45 plus 0.57 whole square, which comes as 2255.21 kilonewton. This is the shear force. What about the permissible shear stress? Permissible shear stress .25 root FCK equal to 0.5 root over 20 equal to 1.118 Newton per square millimeter. So we are getting this value tau P equal to, shall I write down once more here? Let me write down here. P by L square minus A plus D whole square equal to 4 times A plus D times D tau P. Therefore, tau P equal to P by L square minus A plus D whole square divided by 4 times A plus D times D. So we can write down here as P by L square, this part already you have done, that is the your shear force, which is coming as 2255.21 divided by 4 times A is 0.45, D is 0.57 times 0.57. So we can find out tau P, that is equal to, here we are getting 0.969 less than 1.118 Newton per square millimeter. So indirect way we are doing. The other way you can do it that directly you can compute that you put the value of tau p and then you find out the d. The way we have done it for one way shear, but here since already we have got it, so it is better to check it with this value say tau p. If it is greater than the 1.118, then we have to increase the depth. Now what about for depth for bending? So here where we have to calculate the moment at the column face. So this one will be equal to, this is your L and this is your A. So L minus A by 2 moment at the face of the column we can write down it as mu. So P by L square times L A square by as per this which is coming as, so this one L minus A by 2 WL square by 2, L is here L minus A by 2, okay. So we are getting here this much. So mu equal to 2550 divided by, I can take it here, okay. So let us write down 3 square, 3 times 3 minus 0.45 whole square by 8, which comes as 690.89 kilonewton meter. This is your mu. Therefore we can write down d here itself. D will be equal to the same formula, mu by 0.138 FCK times a B. B is here nothing but L. B is nothing but here L, because we are talking that L here. So 690.89 into 10 to the power 6 divided by 0.138 times 20 times 3000, and which comes as 288.86. You can understand that it is very less. So if we start with this one, then again we have to recalculate, and that's why it is better always, you can find out that always start with the one way shear so far the footing concerned. So D is required from the bending point of view only 288.86, and your from one way shear we have got it 570 millimeter. So we have to provide that, say 570 millimeter, that we have to provide. Now we have to provide the steel area. So we can find out that the same way, x by d we can find out, or xu by d, 1.2 minus 1.44 minus 6.6 mu by FCK B d square mu equal to 690.89 kilonewton, FCK 20, D 570, B equal to L equal to 3000 millimeter, 6.6 mu, let us break it separately, FCK BD square equal to 6.6 times 690.89 into 10 to the power 6 divided by 20 times 3000 times 570 square equals 0.2339. This part is 6.6 mu by FCK BD square, so 0.2339. So what about x by d? X by d we can calculate as, we can put it back here, x u by d, so we can find out x u by d here. So x u by d equal to 1.2 minus root over 1.44 minus 0.2339 equals 1.2 minus 1.098 equal to 0.102. So x u by d we have got it as 0.102. So lever arm Z equal to d1 minus 0.416 x u by d equals 571 minus 0.416 times 0.102 equals 545.81 millimeter. Area of steel is, say here, due to moment 690.89 into 10 to the power 6 divided by 0.87 times 415, that Fy, times the lever arm 545.81, which comes as 3505.9. We can write down 3506 square millimeter. Provide 12 numbers 20 torr, which comes as area of steel 3769 square millimeter. Here one thing you please note, I have written 12 numbers 20 torr. You can mention like that, but if you make it say here, instead of taking the whole length, I have always considered that length equal to 3 meter. One way you can do it, the same thing you can do it, that bending moment or shear force you could compute for say 1 meter length. When you are talking this one, we can go to the say 1 meter length. In that case, we have to provide that say 20 torr at the rate of certain spacing. Whenever we are talking say 1 meter, but here we have taken the full length, and that's why I am giving the, specifically I am specifying the numbers. Other alternative, that one, that instead of taking that whole 3 meter length, I can take it as if we are taking 1 meter width only, and for that we are calculating the area of steel. So in that case, it is customary to provide in such a way, that means 20 torr of say certain spacing, that we generally. That's why in the slab, whenever we have designed slab, we have taken 1 meter width, and that's why we are providing at the spacing. But whereas in beam, that we are taking the full width, we know the definite length, and that's why we are providing the numbers. So however it is applicable that you know the full length, all those things, so you specify the exact numbers. But where you are only calculating on the basis of a unit area or unit length, then you specify a spacing. Okay. Now we have to check certain development length. So what we can do, there is one thing we can find out here, that if this is the bar, what we generally do here, this is the permissible stress is sigma s. So acting on this pi by 4 phi square. So sigma s is the permissible stress, say for pulling you can say. So, and times pi by 4 phi square. So, that is the one that force that is developed, force that is permissible. You are pulling a bar, so how much is the permissible that you say force? That will be the cross sectional area times a sigma s. Now, I am just trying to pull it like this. That means here if I just make it like this and you are trying to pull it, so what should be the development length? That means there is surface also, there is some stress developed due to my say pressure like this. So, that one should be resisted, it should resist the pull. Do you follow? So, what I mean to say, so now what should be the length? So, here if this one we call it say ALD, this one if we call it ALD, so what is the area? Area will be equal to then pi phi, that is the pi phi this one times this length times the bond, if we call it say bond stress, whatever developed, so that is tau BD. So, if the length is say for example how much I have to do it, so what is the surface area of that one say cylinder or whatever you call it, surface area of this cylinder is equal to pi phi times the length whatever I am just holding and then permissible stress, that is say tau BD. So, in our case it is, so I can write down at here pi phi times ALD times tau BD equals sigma s times pi by 4 phi square. So, we shall get it here ALD or development length equal to phi sigma s divided by 4 tau BD. So, ALD equal to phi sigma s by 4 tau BD. So, which comes as, now I can refer a code clause page number 43 and 42. So, you will get it in clause 26.2.1 page 42 IS 456 2000. Okay. Now, what about tau BD? So, grade of concrete and tau BD, that is the design bond stress. For M20 it is 1.2, M25 1.4, M30 1.5. So, like that we have M20, M25, M30, there is M35 also, I think I can note down here, M35 that is 1.7, M40 and above it is 1.9. So, you can note that it is maximum 1.9 and M20 for our case it is 1.2. Now, this is valid for, because we have taken this one, that surface, this surface we have taken, that is say plane, the surface we have taken plane, not the ribbed one in the say deformed bar. So, what is code saying, that for deformed bar you increase with 60%, whatever LD you will get it. So, that means for that LD will be reduced. For plain bar, mild steel bar, whatever you will get it, and then for, so your bond stress will be increased by say your say 60%. So, you multiply it with 1.6. So, in other way LD will be reduced by, so divided by 0.6, we have to consider that way, you can consider. So, generally we take it say tau BD equal to 1.2 times 1.6 and you can find out. In addition to that, it is easier to pull rather than push. So, in that case for compression you increase that further, you increase by 25%, this bond stress you increase by 25%. So, for plane one surface it is given 1.2, and also for pooling, for tensile, if it is compressed for deformed bar, you increase this one by 60%, so multiply it with 1.6. If it is a compression, then you further multiply it with 1.25. So that one will give you that one. So that tau BD, you take it for the case whatever you are considering, whether it is under compression or whether it is under tension. Okay. So for 20 millimeter torr, LD equal to say 940 millimeter. We can get this one in SP16 also. Whatever I am trying to do, all the problems, I am trying to do it from the first principle using equations. But in other way, but when design office, most of the cases we use say SP16, the special publication 16, that we can do it. So from there also you can find out this chart, 20 millimeter torr, LD equal to 940 millimeter, that also you can take it. Okay. So what about the, then you say, what about your say putting that your, what is called, that how shall we provide the reinforcement? The reinforcement we provide here. So there should be main reinforcement, and that should be in both ways. And so I can say this one we have used how many? We have got it 12 numbers. So 12 numbers, 22 are both ways. We can provide this one say 25 millimeter torr, that we can provide it here. So this is called starter. The starter bar we can provide, and this one will be your say the development length. This is your development length in tension. So we shall get this development length, that how far we shall go, and then we shall provide the column bars. The column bars will go from here, whatever bar you are providing, and at least you have to provide three links, 1, 2, 3 at least you have to provide, and that one should be equal to say 8 torr, at least if it is not specified, at least you have to provide say 300 millimeter center to center, at least 3 tie, stirred up, we call it here tie, that you have to provide. The ring type, it comes like this. To hold these starter bars, you have to provide, and later on that that column bars will start. This is your column bars. This is your column bars. So this reinforcement you have to provide. And what about your overall depth? Overall depth equal to say 570 plus 50 plus this one, we are getting 50 plus 20 and plus 20 by 2. We are taking this one because the other way also you have to provide. So one way you are getting 570, we should not stop it here, because for your one way, that is the one 570 minimum. So if we take, if this is your one side bar, the other side we are having this one. So the center line of this one, and this is your clear cover. So this length is equal to 50 plus 10, 60, but effective depth, for that we have to take it this one, because this is the one that effective depth we have to consider, because otherwise also it may fail. So that's why this is your effective depth. So 570 plus this 10, that 20 by 2 plus 20 plus clear cover. So we are getting here 650 millimeter. So overall depth, that is 650. Now we can make it slope, other things also we can do it, but this one we are talking say square footing with this type of thing we are talking, because we can reduce the this one also we can further we can reduce it. So that also, but anyway we have not, so far we have not considered that in our calculation, but we can further we can reduce it, say like this. So we can find out, and it should be minimum 150. 150 is the minimum, we cannot go beyond that. So 150 is the minimum that we have to provide if we make it slope. So again we have to calculate that effective depth, all those things here, and that is a separate issue. But here we have considered that one constant depth throughout. Okay. So I think we can stop it here today. So